Hey, this is Dr. B, and in this video we're going to solve a free response question for AP Chemistry from 1982. This has to do with chemical bonding. Let's begin. It asks to draw the electron dot structures for the carbonate dianion, carbon dioxide, and carbon monoxide. So let's go ahead and do that. There's three resonance structures for the carbonate dianion. Begin with recognizing that carbon tends to form 4 bonds and oxygen 2. However, we can do that for this top one. See, we have oxygen with its typical 2 lone pairs and 2 bonds, meaning that we have a full octet for oxygen. If you include both lines as being worth 2 electrons, that makes 2, 4, 6, 8. Nice. It also has its 6 valence electrons. If you take a look at the bonds recognizing that they're being shared and therefore counting them as 1 electron, we get 1, 2, 3, 4, 5, 6, meaning the 6 valence electrons are satisfied, so no charge. Perfect. However, for the 2 bottom ones, although we do have a full octet, which is the most important thing, 2, 4, 6, 8, if you count up the shared electrons, we have 7 right here. That one shared electron makes it 7 is how I should say that. And so we have 7 there. That's 1 extra, so we have 2 negative charges. Helping that is the fact that it's resonance stabilized. We can bring in that electron pair and kick that one out, and this is equally likely. It's almost like the same thing rotated, as is this one. In other words, that double bond is spread out between this top oxygen and the bottom 2. The charges are also spread out, so they're not a full negative charge each. So each resonance structure is equally likely. Carbon dioxide is shown below. That's not too bad because in this particular case, we can draw each atom having both a full octet and no formal charge. Notice oxygen with its 2 lone pairs, 2 double bonds, carbon with its 4 bonds and no lone pairs, a very reasonable structure. We can draw a couple of weird resonance structures where we bring out one of these lone pairs. Since oxygen's more electronegative than carbon, it's not totally unreasonable. We still have a full octet, but these charges make this structures 2 and 3 less likely. Finally, carbon monoxide cannot be done that well. Here, we'll show a couple of possibilities here. If you take a look at this, well, number one, I don't even see 4 bonds on carbon, and I see way too many bonds, it looks like, on oxygen. However, we do have a positive charge here, 1, 2, 3, so we're 1 short, and we have an incomplete octet. Here, it's not so great. Let's take a look at each of these resonance structures in detail. Analyze each one to see if it has a complete octet and a formal charge, and pick our favorite. Okay, here we go. Complete octet, no, it's short. Can you see that? 2, 4, 6. Complete octet, oops, it's extended. 2, 4, 6, 8, 10. Yuck. Formal charge, yeah, they both have it. So on all 4 counts, this is a lousy resonance structure. If we throw these electrons in and that one over, well, once again, we got 2 charges, which I don't like. But the reason we're going to see that this one is favored is because check out the full octet. 2, 4, 6, 8, good. 2, 4, 6, 8, good. I really don't like the fact that the carbon, which is less electronegative, has the negative charge, and the more electronegative element has the positive charge. However, the primary criteria for stability is the full octet, and they both got it. Smile, smile. Therefore, this will be our favorite one. Have a look at this one and give it your own analysis. Let's focus on the most important thing. Full octet. Yeah, 2, 4, 6, no. Full octet, yes. But that frowny face right there is going to dominate. Neither has a formal charge, so you might be tempted to choose it. However, the preferred resonance structure is the central one. Take-home message, a full octet preference will dominate your choice. Finally, parts B and C, which has the shortest bond length? Carbon monoxide, clearly, because it has the triple bond. And predict the molecular shapes. This is VSEPR. Let's predict the shapes. Well, the first one, carbon, the carbonate dianion, is an AB3 system. You can see that right there, with no lone pair on the central atom, so that's going to be trigonal planar. Carbon dioxide is an AB2 system with no lone pair on the central atom. They'll spread as much as possible and go linear. And you could also mention that this is sp2 hybridized, or this is sp hybridized. Not necessary, but a nice add-on. And finally, carbon monoxide is simply an AB system. So regardless of lone pairs, any AB system has to form a straight line, and therefore it will be linear. This is the solution to a 1982 free response question.